So good morning all. So today's topic is clocked SR flip-flop. Means we are providing a clock pulse to introduce the clock and control input in a basic SR latch. So first I am drawing the circuit diagram of clocked SR flip-flop by using an NAND latch. So first I am drawing the circuit diagram. So this is the first NAND gate. This is the NAND gate 2, and the inputs are providing by using two NAND gate. This is S input, this is R input. We know that for the case in the case of NAND SR latch, first input that we have to give is S and the other input is R, and this output is Q bar, and the feedback connection is provided by the Q bar is connected to the input of the gate 1 and Q is connected to the input of gate 2. So this is basic unclocked SR NAND SR latch. Now we have to introduce one clock. So the clock that we are giving by through the NAND gate 3 and 4. Here we are applying the clock pulse. CLK, the short form of the clock. We are giving the rectangular clock pulse, and correspondingly the block diagram of clocked SR flip-flop is two input S and R and the output Q and Q bar. So this is the block diagram of clocked SR flip-flop. And one more thing that we have to introduce is the clock pulse. We are writing the clock pulse. Clear? Now the working of this flip-flop, SR flip-flop, is exactly same as the unclocked SR latch. The only difference is with this circuit diagram is this circuit will operate according to the clock pulse. Okay, so we are giving, first I will draw this rectangular pulse that we are giving. As we have seen, there are two spikes. One, when the transition goes from this is low 0 to 1, this is called positive edge of the clock pulse. It will remain in the high, and when the transition goes from 1 to 0, this is called the negative edge, negative clock pulse. So this is positive clock pulse, positive edge, and this is called the negative edge of the clock pulse. So this circuit will respond only when the clock goes from 0 to 1, only when the clock goes from low to high. Now we have to understand the circuitry or the working of this clocked SR flip-flop. Again, we have to take the truth table. We are drawing the truth table for this clocked SR flip-flop. So I am drawing the truth table. For the truth table, we have the inputs and the outputs. The input that we have, before applying the input, we have to apply the clock as well. This circuit will operate according to the clock. This is the clock, the inputs S, R, and the output Qn plus 1. And last is the action. So we are just adding the one column for the clock, and other column remains same as the unclocked SR flip-flop. So first that I am giving in the clock pulse that if the clock is low or when the clock is 0, sometimes you can low you can show by this arrow as the downward arrow. In some books you can find this when the clock is low or when the clock is low by this arrow sign. So anything that you can use. So when the clock is off or the clock is low, in that case I have already told you when the clock is low, circuit will off. This whole circuitry will remains off. So whatever be the value of S and R, whatever value you are giving to the SNR, if the circuit is off, then it doesn't leave any impact the value that you are giving SNR to the circuit. So the cross sign means whatever value you are giving to the SNR, circuit remains off. So when the clock is low, the circuit does not depend upon the value of SNR. So whatever value you are giving, circuit remains off. And in the off condition, the output that the flip-flop will store is the present state or the memory state. That means it remains in the memory state. The value it already stored in the circuit, it will remain in the same state. It will store the same value, that means Qn, and the action that the flip-flop has performed is no change. There is no change in the output. Clear? When the clock is low. Now the second case, when the clock is high, or when the clock goes from 0 to 1. So sometimes you can denote it as upward arrow, means the clock is high. So when the clock is high, circuit will become on. And if the circuit is on, then it will depend upon the value of SNR. So the possible combinations of SNR will be 0, 0, 0, 1, 1, 0, 1, 1. Clear? This is all for when the clock is high. When the circuit is on, then it will depend upon the 4 possible combinations. So output will depend upon 4 possible combinations. So again, we have to take the 4 possible combinations when the clock is high. So first case that we are taking when S is 0, R is 0. When S is 0, this is 0, R is 0, and the clock is high, means the clock is 1. Clear? So now we have to keep in mind the truth table of the NAND gate. We know that according to the condition of NAND gate, NAND truth table, what it says that we can write it, or if you know the truth table of the NAND gate, if any of the input is 0 in the NAND gate, any of the input is 0, output is 1. So that corresponding output is 1. This is 1, this is 1. Okay. Now to solve this circuit operation, we have to assume the value of Q. Let's say we are taking Q as 1. If it is 1, then this should be 0. This 1 comes here. So 1, 1, according to NAND gate, this is 0. This 0 goes here. So 1, 0, output is 1. So means you have assumed Q as 1, and for the next cycle you are getting the same Q as 1. Means again when S is 0, R is 0, it will store the last value. Means no change. Again it will remain in the present state or no change state. Clear? Again no change, or it is in the memory state. Now the second input condition that we are taking is S is 0 and R is 1. So we have to erase this first. When S is 0, R is 1. S is 0, R is 1, and the clock 1. Clock is high, so clock is 1. Okay. So S is 0. In that case, we know that any of the input is 0, output is 1 according to NAND gate. So this is 1 and this both are 1, the output is 0 for the NAND gate. Clear? Now we know that any of the input is 0, output is 1. So this 1 comes here, the output comes 0. So S is 0, R is 1, switches the output as 0. Qn is 0, and whenever the output is 0, I already explained, whenever the output comes 0, the flip-flop will perform the action of reset. It will reset the flip-flop. Clear? Now the third input condition is S is 1, R is 0. So S is 1 and R is 0. So the third input condition is S is 1, R is 0. According to NAND gate, if any of the input is 0, its output becomes 1. And if this is 1 and the clock is high, the clock is 1 here. So both the inputs are 1, output is 0. So 0 here, 1 here. Now what we can conclude, if any of the input is 0, irrespective of the second input, output will be 1. So this is 1, this 1 comes here, both inputs are 1, output will be 0. So S is equal to 1, R equal to 0, switches the output to 1. And whenever the output comes 1, flip-flop will perform the action of set. And the last input condition is with both the inputs are 1. If both the inputs are 1. So S is 1, R is 1, and the clock is also 1. So do you know that if both the inputs are 1, output will be 0. Here 0, here 0. And we know that according to NAND gate, if any of the one input is 0, whatever may be the other inputs, the output will always be 1. Means the output comes to be the same value. So that I already told you that this is the condition of don't care, because flip-flop will confuse which value it has to store. It violates the basic definition that both the outputs must be the complement of each other. So that state to be the forbidden state. We never want to impose this input condition that S is 1 and R is 1, because it will not match with the basic definition of the flip-flop. So as we have already seen that this working is same as the unclocked SR latch. All the actions are same. The only difference is the circuit will operate only when the clock is high. Otherwise circuit will not operate. So this is all about the clocked SR flip-flop. Thank you.